So I'm writing it down in Boyer-Lindquist coordinates. So this is usually, I'm bound to misspell this. This is usually the way that we write down the Kerr solution. And I've chosen to write it looking like orthonormal. But again, there's more than one way that you can do this. This particular orthonormal basis highlights the structure of the event horizon. So I need to tell you what these functions are. So A is measuring an angular momentum. And so what does A do? Well, it modifies some of the potentials. You see that, you sort of get, in Schwarzschild, this delta would be r squared minus 2gmr, goes to r squared plus a squared. So that's the sort of modification of potentials. But I think most crucially, you see in the t and phi parts of this orthonormal basis, if A is non-zero, you get these cross terms. So this is kind of the smoking gun of rotation. In that, if I time reverse my solution, send t goes to minus t, then you can see that the metric is not invariant if t goes to minus t. But if I send t goes to minus t and a goes to minus a, then it is invariant. So that's saying, well, I reverse time and I reverse my angular momentum. So these pieces, if you like, are the indicators of rotation, these off-diagonal terms. Now our event horizon is given by delta equals 0. So I said that this structure sort of brought out where the event horizon was, and it's really because this is kind of an equivalent of a local dt, a local time, and this is where the prefactor is going to 0. That's not the same as gtt goes to 0, okay? So the event horizon, so that obviously occurs at r is gm plus or minus root gm squared minus a squared. So we've got two roots now. So you've seen that with Ryson and Nordstrom. They have, haven't they? Yeah, it was in one of the tutorials last week. So there are two event horizons here, an inner and an outer event horizon. And then we've also got GTT tends to 0, and brilliantly I didn't write it down. Am I going to do this on the hop or not? So if GTT goes to 0, that tells you that delta equals a squared sine squared theta. And this is called the ergosphere. What it means is that once you're inside this radius, you cannot remain at rest relative to infinity. So you have this structure of an event horizon, and then the ergosphere, you can see it's fattest at theta equals pi on 2, and this is the axis of spinning of the Kerr black hole. So this is kind of what a Kerr black hole looks like. So there's something to notice about this. It's a vacuum solution, but it's only got two parameters, m and a. So there's two parameters only. So there's not a lot of information. Our black hole is characterized by two numbers. And so if you think about the black hole now interacting with other systems in the universe, you can imagine, if you want, just throwing all your garbage down into the black hole, and then you get rid of it. It's like you've wiped it out of existence. So that seems to be quite a bizarre sort of property. And typically, in physics, you expect, as time moves forward, that the disorder of your system increases. So this was really how people started to think about black holes in thermodynamics. There was this, on the one hand, a notion of standard statistical physics, where you have entropy, which gives you a notion of disorder in a system, and you could then imagine in the universe throwing your disorder, sweeping it into the black hole and getting rid of it. So where did the disorder go? Where did the entropy go? So let's have a look at what happens if you throw stuff inside a black hole, one of these black holes. So the area of the black hole so R plus is the outer event horizon, so I suppose I should have labeled those horizon radii R plus or minus. So if I look at the variation in area when I throw something in, then it's going to increase, presumably. We'll see. In fact, it does. And it changes as R plus changes, and it changes as A changes. So we have to add up the effects of both of those shifts. So R plus, we can see that that is just given by delta of R plus there, so that's G delta M, and then it's taking the square root. Minus A squared. Right. Yes, Tibra.
What does it mean, the ergosphere?
The ergosphere. So the ergosphere, it's from, this notion of motion, ergo. So it's simply saying that inside that region, once you're inside this radius, you cannot remain at rest relative to, so asymptotically far away, this is Minkowski space, it's an asymptotically flat metric. So T is the time at infinity of an observer infinity. And so if you try and remain at rest, so usually you can remain at rest relative to infinity, say in a Schwarzschild black hole, by simply having a strong enough rocket to sort of, it's a bit like those, the boats near the Niagara Falls, where they kind of seem to remain at rest, and you can tell their engines are full blast, because of the current that goes downstream. And so it's the same thing with the Schwarzschild black hole. But because of the rotation and the fact that this rotating black hole is kind of dragging the space-time round with it, you can't remain at rest once you get inside that region. So that's what it's...
But can you still escape to infinity?
Yes, you still can escape to infinity. So you've kind of got to go with the flow a bit, sort of allow yourself to be spun round, and then sort of just try and get out transverse. So, one thing I was going to discuss with Tibra was whether, maybe doing some geodesics with Kerr might be a good tutorial project. So yes, you can still escape. Mm-hmm.
What's the meaning of the inner horizon?
So just like with, it's a good question. Just like with Rice and Nordstrom, you have this other null surface inside. I think the meaning of inner horizons, obviously, if you tried, going there might be a bit of a one-way ticket, okay? one of the things that they are special surfaces in the exact solution once you extend beyond the event horizon. One of the problems with inner horizons is they tend to not be well behaved under perturbations, so that if you throw a little bit of matter into the black hole, what it looks as if it happens is that matter kind of all piles up and blue shifts on this inner horizon, creating some sort of, I guess, weak null singularity. So although they're there in the space-time, the mathematical structure of the space-time, it's not that clear whether physically, that they have a significance. What the inner horizon is telling you more is that inside these black holes, the singularity is time-like, whereas inside the Schwarzschild black hole, it's space-like. So once you're inside the Schwarzschild black hole, you smash into the singularity. Whereas the maximally extended, well, Rice and Nordstrom and Kerr, there's this sort of, you have this sort of, you're led to think that maybe you can go in and you can avoid the singularity and come out into a new universe. It's great stuff for science fiction, but it's not clear whether that's actually a sort of physically sensible process. So it's an interesting question to explore, the inner horizon. Yeah. Right, so let me continue with manipulating the area of our Kerr event horizon. Okay, so I've got the pieces on the right-hand side are proportional to delta M and proportional to delta A, so I can just pull these two together. So this is my expression that tells me how the area of the event horizon changes. But, of course, A is J over M. So delta A is delta J over M minus J delta M over M squared. So I really want to look at things involving changes in real angular momentum here. And I'm going to define omega, which is the angular velocity of the horizon. So I'm going to just use that to re-express some of the pieces involving delta A. So if we carry on, delta A over 8 pi, let's pull together all the pieces that involve M. So I've got my R plus squared G. Then I've got a delta M coming from this part of delta A. And then finally, I've got a bit that's about the change in angular momentum. So that's where I've rewritten the prefactor in front of delta J in terms of this omega. So now you can see I've got this common factor, which has got the R plus squared plus A squared. So that looks like the area, or the background area. So this tells me So I want to compare what I've derived with the standard thermodynamic relation. du is TdS minus PdV, plus chemical potentials and charges. So here you can see that angular momentum is kind of a charge. This is its potential, the rotational velocity of the horizon. I've bracketed the minus PdV because I haven't really put or considered this term. But you can actually add this term in by thinking about a cosmological constant. And so really, this bit is sort of the bit to focus in on. So during the 60s, after John Wheeler had sort of coined this phrase, black hole, to represent these objects in general relativity that seemed to be a sort of rip in the fabric of space-time. What you threw in didn't come out. People started developing an understanding about black holes and developing theorems. And one of the things that you notice is that if you have positive energy, so just T0 being positive, then, and you throw this stuff into the black hole, the area of a black hole always increases. So it's kind of like a second law there. And so here, this is giving you a relation, if we just ignore rotation for a moment, it's giving you a relation that says if you increase the mass of your black hole a little bit, then the area also increments up. And there's a direct relation there. And if you do the Euclidean trick, or the real McCoy calculation, this prefactor, this is why I separated these out, this prefactor kind of looks like the temperature that you would get, although in reality it was this part more that people argued in the first place. So once you know that that area increases in a physical process, that's giving you the clue that the area of the black hole is something like the entropy. So by adding this to your budget, if you like, of entropy in the universe, by adding area of black hole event horizons, once again, if you summed up the disorder you had in a physical system outside the black hole, plus the area of the black hole, throw your stuff inside the black hole, and then look at the entropy, you will actually see the entropy increases. This A over 4G is kind of the maximal sort of entropy that you can have for a given volume. So what we've done previously was look at Schwarzschild. So if I take A goes to 0, I do indeed get 1 over 8 pi gm. And the entropy is basically a quarter of the area in Planck units. So that's just by looking at classical properties of classical black holes and trying to interpret them as part of a system where they live together with some other thermodynamic system. So now what I want to do is to discuss how you can actually back this picture up by doing a Euclidean calculation. So I should say that there's got to do a bit of caution with this. So I'm putting with caution in brackets because really this is not that well a defined process. We know that, at least from the standard perspective, gravity is not, you cannot quantize gravity. So gravity is not a quantum theory. The only way in which we think we know a little bit how to describe gravity as a quantum theory is sort of within the fold of string theory. And even then, it's really a perturbative graviton type of calculation. So here, there's a sense in which this is not that well defined. However, if you kind of hold your breath and tiptoe through the formalism, you can get meaningful results. It's just that this is not saying you can quantize gravity in this way. It's kind of just a description. Mm-hmm.
So the S equals to A by 4G, is that just for absorption or?
No, it's general. Yeah. Mm-hmm. Well, in this case, I was identifying it with Kerr. So in the context of this particular exact solution. So I guess I just want to put a couple of flags, a couple of caveats up here. We're going to use this approach. We'll see that it makes sense, for the classical solutions we've got. And I think as long as you remain sort of close to a saddle point, close to a classical solution, there's a sense in which this works. It's not sort of completely valid. Right, so we're going to construct, or typically, you construct a partition function by taking the exponential of minus beta. So beta here is, remember, 1 over t. So I'm taking the Boltzmann constant to be 1 here. And h is the Hamiltonian. So for us, if we are integrating some Hamiltonian density over a spatial surface, then we would say that this is, d3x d tau of our Hamiltonian density. So really, our partition function becomes a trace over the exponentials of minus the Euclidean action. So our four-dimensional Einstein-Hilbert Euclidean action. So, as always, we expect saddle points to dominate this action, which are our classical solutions. So what we saw last time was that the right way to take a gravitational action was to take the standard Einstein-Hilbert term, volume term, of the Ricci scalar, but then to account for the boundary pieces that you get when you integrate by parts by adding an extra boundary term. So this was the Gibbons-Hawking boundary term, which involved the extrinsic curvature. So this should be our Euclidean action. And now we see why this boundary term is such a friend, because if we're dealing with vacuum solutions, then that first term is 0. So if it was just the first term, all of the Schwarzschild solutions, independent of the mass, temperature, etc., would have 0 action, which would not be ideal. So this is the term that could potentially make the whole thing make sense. So let's have a look now for Schwarzschild. So we talked about Euclidean Schwarzschild, and we said that it was something like a cigar. Euclidean Schwarzschild, if times S2, which I'm kind of going to ignore. So topologically, we have our two spheres, and then we've got this closed off little cigar-shaped manifold, which is really just topologically R2. So let's look at a boundary term. We're going to, here's our tau. We're going to place a boundary, delta M, at R equals R, some capital R. So we're going to do the usual thing of setting a cutoff at large R and then explore what happens as R goes to infinity. So remember, delta tau for the Schwarzschild solution, our periodicity of our tau coordinate is 8 pi gm. So this is Euclidean Schwarzschild, which is, of course, I'll just pop it here. So what we want to do is we want to compute the extrinsic curvature of that boundary and then look at the integral over the boundary. So our boundary manifold, delta M, is coordinatized by tau, theta, and phi. The two-sphere for theta and phi has radius capital R, and g tau tau is not quite 1, it's just a little less than 1 for large R. So the normal, if we're going to calculate k, we need the normal. So here's our n. And the normal's in point, and the normal lives in our manifold M. So our normal vector is a radial vector, points straight inwards, and if we want a unit normal, we have to give it a factor proportional to the square root of 1 minus 2gm on R. So now let me calculate my extrinsic curvature, K. K is just the divergence of n. So you can see n just carries on being radial as we extend it inwards. So when I differentiate my r squared nr, I obviously get the derivative of r squared, so I get 2 over r nr. And then when I differentiate nr, well, nr is just proportional to the square root of 1 minus 2gm on r. So I've got a half times 2gm on r squared times 1 over the square root. And so that's why I get these factors here. So that's my extrinsic curvature. Meanwhile, the volume element, or local volume element, root h, is just the square root of 1 minus 2gm on r. And then I've got r squared sine theta coming from the theta and phi angles.
Sorry.
Yeah.
I'm not sure of that term.
The second term.
No,
Uh-huh.
1 over r squared partial r.
So this comes, you mean this piece here. So this comes from the identification of when you have a divergence here of a covariant derivative, this is coming from that relation. I think it was in the first GR course. So here we've got 1 over root g dA root g NA. That's where that one's coming from. So it's often, you can, these shortcuts for taking covariant derivative using the square root of the determinant of the metric can be very useful. So in this case, the covariant derivative is in the higher dimensional spacetime. So it's root g of the higher dimensional spacetime. And of course, I have root g is really r squared sine theta, and I've just not bothered to put the sine theta in because it's only nr that is non-zero. So that's where that comes from. It's a sort of, it's a nice way or an easier way of taking into account all of the connection components that you would get if you wrote down the covariant derivative in longhand. All right. So if I now look at the integral of k root h, d3x, well, d3x is just d tau, d theta, d phi, and the only thing that I've got that depends on that is just the sine theta. So I get my normal 4 pi from integrating over the 2-sphere, and I get a beta from integrating with respect to tau. So I've got a 4 pi beta coming from my d3x. I've then got, here I've got root h, so I've got r squared root 1 minus 2gm on r. And then I've got k. Well, this k is simply this factor, 2 over r plus gm over r minus 2gm. And then I've got nr, and nr is minus this square root, so I square my square root. So if I now multiply through by, if I square up my square root, I've got 1 minus 2gm on r. So overall, this prefactor is r into r minus 2gm, so that's the same there. So if I now multiply through, I get 2r minus 3gm. So that's my integral of k root h. So just a couple of comments. Notice so we've been so enthusiastic about not getting a zero answer, it looks like we've suddenly hopped into having an infinite answer. So this sort of gone a bit too far in the opposite direction. On the other hand, if I just stop a minute and sort of say, but hang on, notice that if I say m goes to 0, I've still got a divergent answer. And so this is a clue that really what we've got is a problem of just a sort of general background infinity. And so what we need to do is to subtract this background infinity. That down, yep. So what we're going to do is to perform a background subtraction. We're going to look at the vacuum solution, set m equals 0. We know that it's divergent, so we're going to properly calculate its divergent piece and then subtract from this Schwarzschild value. So it's not as simple as just deleting the divergent term. Nothing's ever that easy. So flat space at finite temperature is just a cylinder. Here, it's our flat space. Now, the reason it's not as simple as just deleting that 2r term is that you have to compare like with like. So what that means is your boundary metric must have the same behavior. So your boundary metric has to be the same. So remember our Schwarzschild boundary metric, we've got r squared d omega squared, so we've got to have a two-sphere that's the same size, but we've also got to have a time-like circle that's the same size. So the length of our time-like circle has to be this 1 or root of 1 minus 2gm on r. So this T here has same periodicity. Alternatively, you could always say, well, flat space is just dt squared plus r squared d omega squared, in which case, to make it have exactly the same geometry as your Schwarzschild boundary, you'd have to change the periodicity of your Euclidean time. So you kind of have to compare like with like on these boundary manifolds. And here, this is now just a fixed factor. So really, it's saying that flat space is just at a subtly different temperature to the Schwarzschild space, but as r goes to infinity, the two temperatures converge. Mm-hmm.
If I were to write the r part, that would be a different argument.
So you would just add, okay, so you would, oh, I see what you're saying. So that should really be a fixed factor, whereas if you were writing the r part, you'd actually change that to r squared and that to dr squared. Yeah. So it's really as a cylinder, but it's like your normal, do I mean that? Yeah. Yes, it should be r cubed cross s1 for flat space at finite temperature. Mm-hmm. Yes, absolutely, because good point, Tibra, because the extrinsic curvature k, in this case, k naught, is actually equal to minus 2 over r, which is reflecting the fact that, you know, you're in r cubed and that these two spheres are changing, I guess. And n in this case is just minus d by dr. So there's no factor there at all. So our integral of k0 root h in flat space, we've still got 4 pi beta because I've said that I sort of rescaled my time coordinate so it had exactly the same periodicity. And I've still got the same root h factor because I've matched. We expect that because we're matching our boundary manifolds, so I really should have the same root h. But what changes is k, which is now just the geometric sort of flat space extrinsic curvature of minus 2 on r. So we get So we get the divergent piece that we expect, the 2r, but it's not all we have. We've got an extra factor. So the extra factor is due to the fact we have to match these boundary manifolds and the fact that the temperatures are just slightly mismatched at large R. So I now expand to leading order this square root. So if I take my square root to leading order, it's just 1 minus GM on R. And so you see that the background subtraction is not only going to kill the divergent term, it also alters the mass-dependent term. So if I look at the difference, I've got 2r minus 3gm minus 2r plus 2gm. So I get minus gm in there. And so what I finish up with is beta m on 2. So it's kind of one contribution coming from the mass, which comes from the sort of geometric part of the geometric part of your sort of black hole geometry, and the beta comes from your periodicity of time. So there's something coming from both sides, but of course we know that beta is related to m, so we could write this in terms of m, or we could write it in terms of beta. So now let's use this to actually try and calculate the entropy. So we get the entropy by, we've now computed our Euclidean action, we've renormalized it properly, and so we've got this notion of a partition function now. Admittedly, all we've done is compute this for a single saddle point. I mean, technically, you're looking at all possible geometries with this particular periodicity, but we know the periodicity changes if we change the mass. So let's just roll with this and see what we get. So for our class of geometries here, just simply with, in the Schwarzschild class, we've simply got d by d beta of I Schwarzschild on beta, which is beta squared on 2 dm by d beta. But of course, we know that the temperature of our Schwarzschild black hole is 1 over 8 pi gm, and T is equal to 1 over beta. So beta is 8 pi gm. So therefore, dm d beta is just 8 pi g. Sorry, 1 over 8 pi g dm d beta. So for my entropy, I get beta squared on 16 pi g. So I can kind of rewrite that either, as a function of m. So I replace what, the beta is 8 pi gm, and I get 4 pi g m squared. And then all I've done is rewritten that in terms of, I've taken the 4 pi, I know my Schwarzschild radius is 2gm, so I've taken r plus squared there, and then the appropriate factor I get on the bottom is 4g. So in fact, my entropy really is 1/4 of the area. So we've, again, as I said, there's a sense in which this is, we see that this procedure makes sense. It gives, it gives good answers, but I'm just sort of saying don't try and use it, too blindly. It's very good if you're trying to calculate thermodynamic quantities, and works nicely. But of course, we're now left with this entropy to explain. The temperature can be nicely explained by looking at, scattering or looking at the actual states of a field theory in the black hole background. But of course here, from the perspective of classical gravity and also this sort of pseudo-classical Euclidean argument, we really, although we've derived the entropy, we have no understanding of it. We cannot associate this entropy to a number of microstates. So we don't have an explanation for entropy. So that was for a long time one of the sort of problems or open problems in thinking about quantum gravity. Now we do have at least some understanding of this expression now in the context of string black holes and microstates of those stringy black holes. But again, that's in the context of extreme or near extreme black holes, in other words, where there's very close to being supersymmetric. So I think it's probably still fair to say that for your bog standard Schwarzschild black hole, still not really quite there. But at least, there's some measure of understanding of this. Another sort of issue with black hole thermodynamics is that, of course, T, well, I mean, it's equal with our choice of fundamental constants, but T is inversely proportional to M. So dm by dt is negative. The specific heat of a black hole is negative. If we wait, if we sort of bask in its radiative energy, it gets hotter as it radiates. It doesn't get cooler. Then we've got the notion, if it's radiating, it's getting hotter, it's radiating faster, it's getting even hotter, etc., etc. It sounds like a runaway effect. So our m dot, the change in mass of a black hole, is going to be proportional to the area of the black hole times t to the fourth. So it's a standard Stefan-Boltzmann type law. And so this is looking like t to the fourth is 1 over m to the fourth. And of course, the area of the black hole is proportional to m squared. So m dot is proportional to 1 over m squared. And so you can see that the lifetime of a black hole so you've got sort of dm cubed looking like dt. The lifetime of a black hole is proportional to its mass cubed. So it's one of those, it's sort of, as they evaporate, they get hotter and hotter, and then eventually sort of just, presumably, disappear in a sort of big puff of radiation. So the fact that you have this rather spectacular, yep.
Sorry, what would be the lifetime of a solar?
Well, at the moment, there wouldn't, because the solar, I'm trying to remember, is it nanokelvin or something, the solar mass black hole? Any astrophysical black hole has a temperature, or a sort of native temperature, that's lower than the temperature of the cosmic microwave background. So at the moment, all black holes are actually absorbing from the cosmological medium. Well, even then they're not, because they're not idealized vacuum solutions. Most black holes, at least, so astrophysical sized black holes, are going to be in quite a messy environment. They've got accretion disks. There's a lot of sort of interstellar medium around. Your sort of supermassive black hole, that seems to be sort of slightly cleaner, but it's by far from, no way is it like the Kerr solution, completely isolated. There's always some matter there. So you've got, I'm trying to remember whether the boundary's 10 to the 15 or 10 to the 12 Planck masses. It's somewhere in that region. You've got to have black holes, primordial black holes, that were essentially formed in the very early universe out of just fluctuations in, sort of the standard, like you have the sort of standard perturbation spectrum, fluctuations around your background. So primordial black holes are the only possible source of these radiating solutions at the moment. But if we end up with one of these sort of slow, painful universes where it just sort of peters out and goes to some cold state in the future, then of course maybe these black holes could then start evaporating. So just as a final comment, or again, I'm sort of just summarizing some of the questions that thermodynamics raises. So a realistic black hole, or black hole in nature, so a black hole forms from gravitational collapse. We don't have this exact time-symmetric Schwarzschild, or indeed, well, not quite time-symmetric, but idealized Kerr solution. So we have this picture, causal picture, of a black hole forming, where you have some matter that, for whatever reason, just sort of starts to collapse inward under its own self-gravity and eventually falls behind the event horizon. So remember, we said that you couldn't concentrate matter too much without forming an event horizon or forming a black hole. So the pictorial representation of this is something like the following. So here is collapsing matter. Singularity. And this is the event horizon. So the right-hand picture obviously is more of a sort of sketch corresponding with an intuitive notion of what might happen. The matter collapses and eventually all smashes in on a particular point, forming a singularity. And meanwhile, an event horizon forms, and what you're seeing here is actually this is something that you find when you look at black holes. The event horizon starts to form before the matter's gone in and all crunched down onto a single point. So the event horizon is a global property of the space-time. You see it here in this causal picture. And that also can be an issue sometimes when you're wanting to follow messier situations numerically. The fact that the event horizon is this global surface. So here it starts, sometimes you see, if you look at the event horizon of a black hole, if you then put a little bit more matter sort of coming into your black hole, the event horizon starts to move outwards before the matter's actually crossed it. So it's one of these things that's just sort of one of these cute little curiosities. So then, if it evaporates, what happens? So we go back to this picture, the causal picture on the left, and if it evaporates, then what you're left with is something which is a perturbed Minkowski space. So you get something like this. So you've got your scry plus, scry minus, and your horizon. And so this should be the causal picture of an evaporating black hole. This is here, you've got your matter that formed the black hole, and then here you've got your sort of radiation, Hawking radiation, that sort of toodles out to infinity. And so from the point of view of the states, I'm just going to represent this schematically. If you look at the basis, the Hilbert space for your states, you've got the relationship that the sort of past vacuum or the past states is equal to the sum of these two future ones. And so given that this is your future, this is where you are, t equals infinity, this represents a loss of information. Again, this is all following the rules of the game. And so this is one of the reasons that some people are uncomfortable with this picture of black hole evaporation. It represents a non-unitary evolution. You can form a black hole by a pure quantum state, but you expect that it'll radiate into a thermal state, which is a mixed state. And so the issue is, how on earth do you reconcile these pictures with a quantum field theory in which evolution is unitary? So I'll stop there.